I guess, internet protocols, and he's been working on wireless communications and security recently. And his talk today is about real-time visualization of network attacks on high-speed links. So
thank you. Nice to meet you. I'm visiting Professor Ki-Hong Park's lab this semester from Korea University. And as just mentioned, I come from the TCP/IP background, so I'm a networking guy, not really a security guy. But I've done some work in network security a couple of years ago, and this work is about that work. Okay, and the work is about visualizing network attacks. Network attacks meaning DOSes, DDoSes, and worms and scans and things like that. So we are interested in visualizing those attacks for probably network operators. Okay. So the outline of the talk is this. It's a three-part talk. So in the first part, we'll talk about the literally visualizing the attacks. And the second part is about more algorithmic, more automatic stuff that extracts the attacks and sort of classifying the attacks and if possible, calibrating it, measuring the intensity of the attacks. And the third part is sort of an extension to an earlier work. I'm not working on this, but my colleague at Korea University is on it. And it's called PCAV, Parallel Coordinate Attack Visualization. And so we will talk about these three stuffs in this talk. Well, why visualize? We can talk about the shortcomings of the conventional systems like IDSs. It is known that they have issues with unknown attacks. I mean, if they have signatures already, it's fine. But if they don't, I mean, if it is a fresh kind of attack, then they have trouble detecting it. And also, it is also known that IDSs in the current systems have high false positive ratio, meaning it generates a lot of information, but about the possible attacks, but most of them are not true. Okay, so you have to go through all those possible attack reports and find the real attacks. And the outputs are mostly text-based, so you have trouble sort of imagining what's going on. Well, if you use visualization, first of all, it's very intuitive. I mean, it makes you grasp what's going on. Okay, in one picture. Okay, just like the guy looking at this picture. Right? And it's very robust against noise. Okay, if you look at a picture, then you almost immediately get the information that you want from the picture. Okay, you remove sort of the noises, the pieces of information that you don't want. It can reveal the hidden attacks, usually not caught by the conventional systems. We'll see about that later on. And it can also inspire new approaches. And actually, the second part of the talk is about this new inspiration given by this visualization work in the first part. So we can sort of summarize the lessons from this work as a picture is worth 1,000 words. Okay, so, well, how do we sort of visualize attacks? Okay, we talk about DDoSes and worms and scans, but it's not straightforward to imagine the attacks going on. I mean, represented in visual forms. So how do we do that? Well, basically, the idea starts from this observation. Okay, the most interesting attacks that we talk about can be sort of classified in a single framework. If we use these three values: destination IP addresses, source IP addresses, and destination ports. Well, DDoSes or DOSes, if you look at that kind of attack, you will see that the source IP addresses are usually spoofed, meaning forged, in order to evade the traceback. If you look at scans or worms, you will mostly see that the destination port is fixed. The source address is also obviously fixed because there should be the scanner sitting there, but the destination IP address, constantly changes from one scan packet to another, because it has to check, as many vulnerable hosts as possible. So if you look at these three fields, easily obtainable from most of the internet packets, you can classify the attacks in a single sort of framework. So if you sort of visualize this idea, you can draw this picture. Okay, you talked about three values, so we're going to use those three values to generate this 3D space, and the 3D space will be drawn on these three axes: source IP address, destination IP address, and destination port. And if you think about, say, a host scan, okay. Sorry, let's go back. Okay, so if you think about this host scan, the source IP address coordinate will be fixed, and the destination port number will be fixed. I mean, for instance, you might be looking at the vulnerability in secure shell, buffer overflow, stuff like that. And then you will look at port 22. Okay, so the port number will be fixed. But since you're looking, you want to get as many vulnerable hosts from the global internet, you will get in touch with lots and lots of different hosts that have different IP addresses. So if you plot those attempts in this space, you will see a line forming gradually. Okay, you get a point here, point there, but those points will be aligned along a line. Okay. Likewise, if you see a port scan, okay, if an attacker is targeting a single victim and wants to sniff any vulnerability, okay, any open service, then it'll go through the port number space of that machine, target machine, while the source IP address and the destination IP address, is fixed. Okay, so that's our idea. The rectangle is a kind of DOS, but depending on the software or the script, the destination port number can be spoofed, quote unquote. But that's, it's not really spoofing, because the attacker doesn't really care about the destination port numbers as long as the attack packets arrive at the destination IP. Okay, so in some cases you'll find that the DOS attacks randomly changing the destination port numbers too. In that case, you will get this rectangle. If you put all those attack packets in this space, plot all of them in this space, you will get this rectangle. That was our idea. And at the time that we came up with this idea, we couldn't check if our intuition was correct. Okay, if this is a viable idea. But from some traces we got, we could sort of get the feeling that the intuition was right, because if you see this particular trace, real life trace from the internet, this is, by the way, a DOS trace. You can see that this is a time. This is 9:35 a.m. and this is the second, and this is the microsecond. Okay, so the source address is here, and the source port is here, and this destination address. We sort of sanitized the destination address in order to not reveal the identity of the victim here. And you can see the destination port. If you see the three values we mentioned earlier, this one, and that one, you can see that only the destination address is fixed. By the way, x.x.x, they're all the same addresses. So only the destination address is fixed, while the others are moving, changing all the time. And in case of scans, again, we sort of sanitize the identity of the attacker. And if you see the destination address and destination port, these two are fixed, while the destination IP address is constantly changing from packet to packet. Okay. And also, one thing that you might notice here is that, that if you look at the destination address, it doesn't stay in a target network very long. It throws 7 packets or 5 packets to that network and moves to another network. So from the perspective of the target network, it'll see some strange packets, like 7 packets, and you wait some more time for more packets, but they won't arrive for a long time. So from the perspective of the IDSs or attack detection software, it sort of raises an issue, because if you have a very low threshold, then you will generate a lot of false alarms. So if you're worried about it, you raise the bar. But in that case, this kind of attack can circumvent it, because it doesn't have too many packets in an attack. Okay. Okay. So later on, fortunately we got our hands on some trace. It was the trace from 2 T3 links connecting Korea's Internet Exchange and United States. Korea Internet Exchange is one of the 4 major hubs for Korean Internet. And as to these 2 T3 links, they were half full at the time we collected the trace. So we could check our idea, the intuition, against this real life trace. Okay, it was collected over a 7-day period, and it amounted to 1 terabyte of data. We had this NDA, a non-disclosure agreement, with the KICS, and subject to that, we could analyze many aspects of the traffic. Okay. So this is what we got. Actually, when we got the trace, I let my master student to go ahead and draw a piece of trace using the 3 values observable from that KICS trace, and he reported to me saying that I see some lines, and immediately I realized that our intuition was right. The lines are text. Okay, so recollecting what we saw before, what do you think this is? A big rectangle. It's a DOS. And what are the lines on the bottom here? Actually, they are not entirely on the bottom. It's actually floating just above the ground. It's port 80. Okay, so since this is a 64K large, so it looks like it's on the bottom, but it's not. So these are scans, and these are also scans. What about these vertical lines? They are not all of them are port scans, but some of them are port scans. Okay, so actually you can see the attacks in one space. All kinds of attacks are plotted. Okay, and you can see the traffic going back and forth in the entire internet. The view oval from this particular location. Okay, so when we saw this picture, we realized that we got the right idea. Okay, and I guess we want to see. I want to see the entire days worth of this picture. From 9:35 a.m. to 5:20 p.m. It'll take about a minute. It's like an animation. Okay. Yes. Okay, so we'll see. We'll start from 9:35 a.m. And here you'll see the the time index. So it's 11:29:35. Okay, so the time flows there. So one frame is 1 minute, and each minute we have like 2 million packets plotted on the graph. So if you see, DOSes come and go, and it seems that the scans remain very long time. I mean, it goes on and on and on over a whole day. And you see that there are some vertical bars too. And all the rectangles are DOSes with destination port numbers also being filled with random numbers. So it looks like changing. Okay, I guess it's enough to see. Okay, so stop this and go back to the presentation. So why do we see so many attacks? Well, it was back in 2001, and the Korean government and the guys who were running the government network and in this exchange were not that security savvy. They were putting a lot of money to expand the Korean internet, so they were making all kinds of broadband connections here and there. But well, one analogy is that they were making highways, but there were no policemen. So a lot of hackers came into Korean internet and they launched the scanning attacks and DOS attacks, whatever you see in there. So this graph shows that how many attacks were there. So the x-axis is the time in the units of 10 seconds. So it starts from 9:35 and then ends at 4:20 p.m. And the y-axis is the number of connections observed at each time instance. And if you see at the bottom there's a line, and this is what we estimate the number of connections, the legitimate connections, okay, at each time instance. And if you see, if you see the top, you see this line with a lot of spikes, and we manually checked the trace, and we found that these spikes are DOSes. Okay, you saw in the previous animation that DOSes were coming and going. They were very short-lived DOSes. Okay, it was not like in a massive attack or anything like that. It's like a test run or some, I don't know what that was, but it was very short, 1 or 2 minutes. So they come and go like that, and the bulk of the attacks are scans. Surprisingly, the scans, there are so many scans, and actually the statistics shows that unfortunately Korea at that time was the second after United States to generate the scan traffic. So there are a lot of scan traffic here. And another question is, okay, there were so many attacks in the trace, but why do they strike out? I mean, there are so much legitimate traffic there, okay, ambient traffic. But what is the reason that the attacks manifest themselves like that? Well, the reason is this: in that space, legitimate flows appear as a single dot. Think about their coordinates. Their coordinates are from their headers, and the headers, in particular, the source IP, destination IP, and destination port. They do not change over the lifetime of connection. They remain the same. So no matter how many packets you have in that flow, you could have a million packets to download a movie, but those three values will remain the same, and every packet will hit the same location in that space. So you will get a single dot for a legitimate flow. But for attack flows, they change 1 or 2 fields from packet to packet. Okay, every packet has 1 or 2 values different. Okay, so they sort of move in that space and generate this geometric shapes. Okay, so doesn't really. It's not that the legitimate flows is really, small in quantity in terms of the number of packets. It's just that, the attack flows sort of inflate themselves and manifest themselves in this space. Okay, and that's a good news to us. Okay. Okay, so far we have seen this visualization idea. So it seems to be cute, but the question here is that does that visualization method inspire any novel approach to detecting attacks? Actually, you can see that figure here after it happened, but can it draw the picture in real time? The answer is probably not. Especially if you have a thick pipe like OC192, for every arriving packet, if you want to draw a dot, that's out of the question. Okay? That's one problem with that visualization when we want to use that for the real attack detection software. The second and more fundamental problem is that it can hide some low intensity attacks and the attacks in the close proximity of the legitimate traffic cloud. Okay, if it is hiding there, then you cannot see it. Okay, but there's an idea that we can actually draw from that visualization stuff, and it turns out that the idea can in fact not only visualize, but it can detect and classify and measure the intensity of those attacks. And it can be done quite fast, so it can run on high-speed links and in real time. So in the second part of the talk, we'll briefly look at that. Well, the idea is that the only attacks appear as a regular geometric entity in that 3D space. And they sort of exhibit this sort of quote-unquote pivoting behavior. Of the three values, they fix one or two and then move the others. Okay? So one of those three values, there are things that move. Okay, the coordinates that move. So we can detect that pivoting patterns and sort of exploit that property to get only the attacks, okay, while ignoring the legitimate traffic. So how do we pan out this pivoting behavior? First, let us define a flow to be a three-tuple consisting of source IP address, destination IP address, and destination port. And then we define the signature for a packet, and the signature corresponds to the flow three-tuple. But the values here will be binary. So KS, KD, and KP, they're all binary. And the binary values tell you whether or not you saw the corresponding value in the flow three-tuple recently. Okay? If you saw the value recently, for instance, if you saw a particular destination IP address recently, then you generate 1. Okay? If not, if you don't remember seeing that value, then you generate 0. Okay? And the question is, how recent is recent? We'll talk about that later on. But basically the idea is that if you see a 0 in a packet's signature, that's where the movement is on. Okay? So you want to catch the movement, right? Because if dots move, that draws a line, that draws a rectangle, and so on. So you want to catch the movement. So okay, basically this is how the signature is generated. Suppose you got a flow at time t, and source IP address was a 3456, and the destination IP was 5678, and the destination port number was 90. Let's call that flow 1. And at time t plus 1, you see another flow, basically a packet, but packet has this flow information. So 1, 2, 3, 4 is SIP, 5, 6, 7, 8 is DIP, 80 is DP. And at t plus 2, you get 1, 2, 3, 4, 3, 4, 5, 6, and 90. So what signature do you give to the third packet? Well, you give 101 because you saw 1, 2, 3, 4 in the SIP position before. Suppose your memory is 2 time units. Okay, it spans 2 time units. So you remember flow 1 and 2. But 3, 4, 5, 6 in DIP position, you don't remember seeing it in the previous 2 packets or flows. 90, you saw it. Okay, so it gets 101, and that's what you get as the signature for this packet. And once you do that, you can define your attack signatures. Okay, for instance, if you have host scan, it's 101. Okay, you see this you keep seeing this source IP address. Okay, and you also keep seeing the destination port, this particular port number. But you see in the same packet, you see differing destination IP addresses. Then you will keep generating this signature for the arriving packets. What about DOS? Well, since they are usually, the source IP addresses are usually spoofed, you will see new source IP addresses, but you will keep seeing this IP addresses, which is the victims. And if destination port is fixed, then you will see the same port number quite frequently. Okay, so like this, you can define the attack signatures. We can talk about it for quite a long time, but I guess we'll stop at that. So you have the attack signatures. One of the attack signatures that is interesting here is what we call Kamikaze. That's 100. And actually we see this strange type of attack in our trace. It was too fast for you to see, but at 512 to 515, you can see actually this rectangle here. Okay, it has the same source IP address, but varying destination IP and varying destination ports. What does this mean? A single source is spewing out packets to so many destinations and to so many ports. Why is it doing that? It doesn't make sense. It's only suicidal, right? It's spewing out, but it's not. It cannot be an attack to anybody. Well, a plausible explanation is that it's a backscatter from a DOS victim. Okay? A source spoof DOS is hitting this poor guy, and he's responding to it. Okay? So it looks like it's spewing a lot of packets to this entire destination IP space. Okay. So we have this attack signature, and how do we implement this in our software? Well, basically we use hash tables. So for source position and destination IP position and destination port position, we have separate hash tables. So when a packet passes, it reads in the appropriate fields, and these hash tables will generate 1 or 0, and combined they will constitute a single signature. When signature is generated, depending on what kind of signature, okay, we have a table here, right? Depending on what kind of possible attack it is, it'll be forwarded to one of the post-processing hash tables in the back end. So why do we use this two-tiered configuration? Because we want to make it run on a high-speed link. Okay, so on the front end, time is the prime objective. Okay, time is. You have a very, very tight time budget. Okay? So what you want to do is you do the quick and dirty check. Okay, you might arrest a legitimate packet from time to time, but you don't want to thoroughly check if a packet constitutes an attack. Okay, so you want to arrest some suspects there from the traffic flow, and you move them to a back end where you have a little bit more time to perform a more thorough check. Okay? So I think for the high-speed network, this two-tiered approach is appropriate. So we checked the speed of the software, and actually we performed a field test on a campus backbone network. At the time of testing, there was 303 bits per second live traffic flowing in the pipe, and we used a Pentium PC, which has had a 2 gigabit Ethernet interfaces, and we ran 2 separate copies on each of on these 2 gigabit Ethernet interfaces, and there was no packet losses. It was reported from the PCAV library that there was no packet losses in the kernel, and we had no trouble processing the packets from this 330 megabits per second live traffic. And the software was quite lousy back then. It was not optimized at all. Okay, it had a lot of junks in it, but it still ran without any problem on this with this speed. Okay, so after doing this, we could check if our extraction algorithm worked okay. So on the left side, you will see the real traffic, the same visualization that you saw earlier. The right-hand side is a result of extracting only the text from the traffic, okay, using this algorithm. Okay, if you see a packet that has this particular signature that matches with one of the attack types, and you throw that into the backend, and where they get this more thorough check, and after that you can sort of derive this this graph here. It's the data is very small here after extracting only the attack information. So I don't think there is any problem plotting this in real time. This was 2 million dots in a single plot, but this is like 20, 30 geometric entities. Okay, so it was quite fast, and you might notice that okay, I see this very slim bar type DOS attack on the left hand side, but you see a very large rectangle corresponding to it. That's because we did a very poor job in handling the outliers. Okay, if you see an outlier, we just draw the rectangle to envelope all of the dots, so that if there is an outlier floating very high up, you will see a rectangle that covers all of the dots. So that's why. And we ran this software again in 2003. We just threw it in some, I don't know, somewhere, and we dug it up in 2003, and we run that software on another trace, and the trace seemed to have this code rate too, and the software had no problem finding it. And this software also generates a text report. It does not just visualize it. It generates a text report for future reference. Okay, so speed seemed to be okay, but one of the things that we couldn't do was evaluate the accuracy of the software, because if you plug that software to the live traffic, you could test the speed, but since you do not know a priori what kind of attacks are in the live traffic, you cannot check whether the software is telling the truth or lie. Okay, so the only thing that you could do is just do the simulation over this software. So you generate the artificial traffic, and insert some attack type traffic, and see if the software catches it. So we generate the sort of quote-unquote internet-type traffic, but it in itself. Generating internet-like traffic is a big problem. It's a very hard problem. Okay, we don't know, how to generate good internet-like traffic. But anyway, we went ahead and generate using the distributions from earlier works, like we generate the ambient legitimate traffic, and we added in the attacks to that traffic, and so if the software catches those attacks. And we measured the sensitivity, relative error, and false positive rate. And the sensitivity is basically, okay, there were 100 attacks inserted in that legitimate traffic, and how many among 100 does the software catch? So that was the sensitivity. Okay, S is the sensitivity here, D is the number of detections, and M is actually the number of mounted attacks. And the result seems to be that, okay, for some types of attacks, the sensitivity is very high. Okay, the x-axis here is the attack rate over threshold. So it means that, okay, if the threshold is set like 50 packets per second, if the attack goes over 50 packets per second, then it's an attack. So if attack rate, has, is set to 1.2 times the threshold, it seems that, what's that? This with the DOS attack with the variable port number are code with 80% probability. Okay. And if you see, there are the two types of attacks that do not have this problem. Okay. And the source of this problem that you have, sort of lower sensitivity, is that when you generate the signatures, if you show it closely, if you see this example, if you see this packet, it has this port number 90, and it also appeared for the first packet, but they are two different flows. I mean, it originated from different source. They are destined to different destinations, but it happens that they share the same port number. This kind of collision in different flows is quite rare in the IP coordinates, because the IP space is huge. It's 4 billion addresses there, so the probability is quite low. But for destination port, it's only 64K, so the probability is quite high, especially because there are quite frequently used port numbers like 80. Okay. So that's why we get sometimes wrong signature for a packet, and that is the reason that we have lower sensitivity for the port number for the attacks that have variable, this one and that one, variable port numbers. Okay. And the relative error is also high for those two types of attacks that have variable port numbers. But fortunately, the port scan is sort of a minor issue from the perspective of the global internet. Okay, large-scale DDoS or a global worm epidemic is everybody's concern, but port scan is between two individual hosts, so it's it's a little bit minor problem. About this DOS with the variable ports. Well, when we started, we sort of split these two types of DOS attacks. But if you come think about it, I mean, you don't have to do that actually. I mean, DOS with variable port, DOS with fixed port, doesn't matter. Okay, they are all DOSes. Okay, so if you sort of remove that this distinction, then the relative error for the DOS attacks with variable port numbers goes down. Okay, so that's how we solve this problem. Okay, we later we found that after we published this paper. Okay, so the false positive rate quickly goes down to almost zero after the attack rate goes over the threshold, and it remains so. Okay, so it has good properties too. So we sort of get the idea from the visualization work about the algorithm that can quickly extract only the attacks from the high-speed flows, high-speed pipes, and how to classify them in real time and how to calibrate the intensities of them. And so that's the second part. Okay, the third part is the recent developments. So I stopped this work like 2 years ago, but my colleague Professor Hee-Jo Lee, who was a visitor here a few years back, is extending this work, and he calls this parallel coordinate attack visualization. Why parallel coordinates? Because I use 3 dimensions, okay? And using 3 dimensions, it has some shortcomings. And he thought that using some more values from the packet headers, he can even he could lower the false positive probability and errors further. So he decided to use some other values from TCP IP headers, like IP datagram length and TCP flags. And also he moved from packet-based operation to flow-based operation, because he thought that it's quite difficult to plug in the software to a router port directly. Rather, he chose this approach that gets the flow information from like Cisco routers, okay, and operate on that flow information instead. So he improved the scalability in that sense. So it's the system that he's designing. He actually implemented it, by the way. So you call these guys that generate flow information sensors, and in this version of the software, he gets net flow input from these sensors, and the monitoring system sort of combines those net flow information but the core engine is similar. Okay, it basically works on this, what attack signatures, and see if there is any attack. But since he extended the dimensions to 4 or more, basically hyperspace, you cannot draw the 3D space diagram like that. The thing that we saw earlier. So he uses parallel coordinates. So a single flow appears as a line here. Like before, a legitimate flow is a single line, but the tags appear as a different shape. Okay, so for a slammer attack, from the slammer attack trace he got this, the first one. From host scans you got this, and so on. So he made the signatures, similar to mine. And actually, let's see how his system works. Okay, so on the top, using this plotting method, he plots entire flows. Among them, there are attack flows hidden in there, and he uses his signature to extract the attacks here. And if you see a particular pattern, then it's an attack, and the attack information appears on the right pane. Okay, so it goes like that. And if you want, you can click on a flow to see the detailed information about that attack. Okay, where it's coming from, and basically the source addresses and the number of packets observed in a given unit time, and so on and so forth. So he has this graphical interface. I didn't have one, but he has. Yes. So, I guess this is the end of it. So to summarize, what we saw is that you can actually visualize your text in a single space, in a single framework. You can see all kinds of text working in that 3D space, and you can actually get an idea from how the pictures are drawn in that space, and using that idea you can devise an algorithm that efficiently extracts your text from the traffic stream and classify them and measure them and visualize them for the convenience of the network operators. And I guess that's it. Okay. So I think I have like 5 minutes. So if you have any questions, I can answer them.
Any questions? For the Kamikaze attack that you mentioned, which you conjectured would be actually backscatter packets, can it not be perhaps verified by checking if there was
Yeah,
a
actually.
attack?
Yeah, that's right. That's right.
Okay.
Yeah, actually, last night I was going through my slides, and then I found that actually I had the same question. I didn't have that question 2 years before, but 2 years ago, but. And then I tried to log into my old system and run the software again, but I failed. I forgot a lot of details about running the software and stuff, and I couldn't find the right trace where it was, so I couldn't check that. But actually, if you see in the same time frame, if you see a DOS attack, you can check the destination of that DOS attack with the source of this Kamikaze stuff, and if they match, it's a reflected image of that DOS. But I couldn't check whether they match. But if you see, there are a few DOS attacks ongoing at that moment. Actually. So if you see, this is one DOS attack, and I know that because it's using this is the class D, class E space. You cannot send a packet to class E space. Class E is reserved for future use, so it's not being used right now. So if you see packets are being sent to that space, you can immediately realize that it's an attack. So it's a DOS attack. So this Kamikaze could be paired with that, but I couldn't check that. Also, it's less visible, but this might be another DOS attack. Okay, and in the background you also see DOS-like figure there, but I haven't checked it. Okay, so you might find a pair. I say you might because there's a possibility of asymmetric routing. Because if you see the sender, it's Korea's IP space here. So the victim is in Korean internet. So the attack might be coming from outside or even inside Korea. But anyway. Where was I? I forgot what I was saying, but yeah, actually you can check.
Okay, unless there are any other questions, let us send the speaker. Go ahead.
We have a question here.
When you analyze this data, did both of you use the same data set, you and the extended work? I'm assuming.
Yeah.
Okay. Did you guys try to? I'm assuming you did it at because the animation you showed us, you said it's every 1 minute increment. Did you guys ever try to do it on a live analysis where every 1 minute you would try to throw out
actually
the system instead of after the fact?
Right. So the test that we performed on the campus backbone was live test.
Okay.
So it was live traffic, 303 megabits per second traffic, and we plugged our software to a router port, and we performed that test, and it actually came up with some attacks, but we could not check if there were indeed attacks, because there's this possibility of false positive, and we do not know a priori if there were attacks. So we had to, if we wanted to check, we had to collect the trace and do the post-mortem, but we didn't do that. We just checked if the software was up to the speed, and it did. So that was it. But you can certainly, we have a version of this software that runs on that can run on live traffic. It has a PCAV library running at the bottom, and grabs packets up, and it hands it over to the software, and it processes it. Okay. So we have a software that runs on a live traffic, and that's what we used for the campus network test. Yeah.
There was a question from our good friends at IU, I believe.
Yeah, can you hear me?
Yeah, go ahead, please.
Okay, the question is, have you had a chance to visualize any, not denial of service attacks, but effective denial of service attacks from legitimate traffic, say a site getting /dotted or dug, and been able to see if there's any way to visualize the difference between a real DOS and a legitimate, so to speak, DOS?
No, I haven't had a chance to do that. But when we designed the software, that we thought that this will run on the backbone. If you move the location of the software to the close to a, say, campus network or enterprise network, to a very popular server, for instance, it'll report that it's getting a DOS attack, because the popular server will be getting a lot of packets from around the world. Okay, and it seems like that it's getting a DOS attack. Okay? So inherently there is no distinction from the perspective of this software, whether between the DOS attack and the flash crowd. But Hyogon Lee's software improves on that too. I mean, when he finds that there's a popular server or a legitimate target that is accepting a lot of traffic, for instance, it uses whitelisting to exclude the target from consideration. So that's what it does. But when we did this work 2 or 3 years ago, we didn't think about using this software at the edge of the internet. We were thinking about using this on a high-speed link in the backbone.
I don't see why it has to be the backbone, though. If I say all of a sudden a site becomes popular because it's posted to on /dot, the traffic's all going to go through the backbone to get there anyway, isn't it?
Yeah, if you see that kind of traffic also in the backbone, I guess this software will report that it's seeing a DOS attack. Mm-hmm. Yeah, so
but I guess what I'm wondering is, a lot of people say you can't disambiguate, but it's possible that the computers that are attacking actually have a different distribution than, say, a botnet. One example might be you expect a lot of IP addresses from North America to attack in a legitimate attack during the daytime hours, whereas in botnet you'd expect the IP addresses, because they're basically spoofed randomly, to come from all over the place. So you might be able to actually visualize the difference between a legitimate burst attack, or a legitimate burst, and a DDoS attack by a botnet.
Well, I don't seem to understand what you're saying. So I guess we can take this discussion offline, maybe, because I guess we're running out of time here. So if you have any questions, please send me a mail. I can.
Yes.
Yeah, because I'm sorry, I don't quite understand what you're saying now. Okay, all right. Okay, any other questions? Okay then. Okay. Thank you very much.